Space and time, as simple as they may appear, are among the most mysterious components of the universe. It may be surprising that time can be bent, stretched, or even stopped, allowing us to journey across the universe within the blink of an eye. This is what I'll be discussing today in this video. Historically, space and time were viewed as two independent entities. It was held that in the fabric of space, time flows uniformly in every part of the universe. In physics or mathematics, these ideas are presented in the form of transformation equations that was formulated by Galileo around 1632. Basically, Galilean transformations try to translate the laws of physics from one frame of reference to another, moving with a constant velocity, such as a train that is moving at a constant velocity. One important thing about the transformation is that it keeps space, in the sense of distance between 2 points, and time invariant. This means that whether you are traveling or standing still, you will measure the same distance between 2 points and the same time difference between two events. No surprise, for normal speeds experienced in daily lives, this concept works very well. Now let's fast forward to 1865, when an English physicist, James Clerk Maxwell, formulated his theory of electromagnetism. The theory proved to be one of the most successful theories based on strong experimental evidences. The main takeaways from the theory are that light is essentially an electromagnetic wave that propagates with a constant speed in vacuum, and that electricity and magnetism are intricately connected, essentially two sides of the same coin. When Galilean transformations were applied to the Maxwell's equations, it was found that the speed of light was not constant, and the transformation failed to preserve the fundamental features of electromagnetism. This posed a significant problem. In 1905, Einstein came with his special theory of relativity, which put forward some of the ideas that would later revolutionize our understanding about space and time. Einstein's theory introduced three key ideas that shook the foundations of physics. First, the speed of light is ultimate speed limit and nothing can travel faster. Second, the laws of physics are the same in all inertial frames. Instead of familiar Galilean transformations, special relativity brings in the Lorentz transformations, preserving a crucial quantity, the space-time interval, not time and distance separately. Special relativity goes a step further, proposing that time and space are not distinct entities, but rather part of a unified four-dimensional continuum known as space-time. Note that the time and distance between two events can change to keep this quantity invariant. Hence, an object in motion experiences time dilation and length contraction, which are essentially the stretching of time and the shrinking of the space. One natural and direct verification of the time dilation comes from the observation of muon on the surface of the Earth. Muons are elementary particles that are created when cosmic rays hit the upper atmosphere of the Earth. Since they live only for 2.2 microseconds before they disintegrate, it is interesting even when traveling close to the speed of light, most muons shouldn't cover more than a kilometer in that time. So here is the puzzle. How do muons regularly reach the Earth's surface, traveling distances of tens of kilometers? The answer lies in Einstein's concept of time dilation. For muons traveling at approximately 99% of the speed of light, their clocks run slower relative to an observer at rest. This causes their lifetimes to effectively increase by a factor of 10 times, allowing them to travel tens of kilometers. Now the inverse is so big, it takes light about 4 years for light to get to the nearest star, alpha-centauri. Similarly, it takes nearly 100,000 light years to get to our neighboring galaxy, Andromeda. It is natural to think that an interstellar or intergalactic journey appears to be incredibly long journey, as it is not possible to travel faster than the speed of light. However, the key is that you do not need to travel faster than light. With a speed close to the speed of light, you can reach any destination in the universe in no time. In theory, you could set out on a journey to Andromeda, have an otherworldly lunch there, and be back home in time for dinner. But here's the catch. When you return, you'll be surprised to see that hundreds of thousands of years have passed on Earth. Picture this: your nth generation descendants mingling with aliens in a completely transformed landscape. Of course, achieving near light speed poses significant technical challenges. Accelerating a spaceship and sustaining high speeds involve complex engineering, possibly taking years. Yet, the mind-boggling implications of special relativity open doors to these seemingly instant space-time adventures. If you were to travel at the speed of light, just like photons, time would not exist for you. And just like for photons, you would be here now and in no time at infinity. From the perspective of length contraction, the entire universe would contract to a single point in the direction of motion, such that you would have nowhere to go. So the next time you gaze at the stars and wonder about the vastness of the cosmos, remember special relativity. It's not just a theory, but a key that could potentially unlock the doors to the universe, because in the realm of space and time, the impossible might just be relative. If you enjoyed watching this video, please share and subscribe. See you in the next videos.